provided I've got the right algorithm.
This meeting is being recorded.
Oh. Provided I've got the right algorithm, I can find my way in one single try out of the maze, which in this case provides more than up to 2,000 times a more efficient solution. If you look at this principle, it's used in many applications, and that was what was difficult for me, because for me, quantum computing is definitely a high performance computing, and numerical simulation is everywhere. And so quantum computing, there are people who are looking at applications in logistics, in finance, in energy, in industry, in health, and they're using different kind of algorithms. So what we will do in the following is just look at some algorithms and then look at how they are used in different. I will provide you with some examples of how they are used in the industry. And there are just a handful class. There are just a handful number of quantum algorithms, and they are stored in a website which is called the Quantum Zoo, which lists all the quantum algorithms that are available. And these quantum algorithms, they are actually used to provide solutions to certain class of problems. And in terms of class of problems where quantum algorithms have strong impact, we can talk about algebraic applications, graph applications, learning applications with quantum simulation, and inverse function computation. So this is really class of problems. And this is really, I would say, classical, or at least standard class of problem where the quantum algorithms provide a speed up, a quantum speed up, and as a result, the quantum algorithms, they provide either a speed up when we solve given problems, and this speed up now, well, I will talk. We can use the power of quantum computing, this intrinsic parallelism I was illustrating in the maze, either to go faster to solve certain problems or to solve bigger problems. That's the reason why it provides, it triggers a lot of interest, because we can solve problems that we cannot solve currently. But there are still some debate on how much speed up is going to be brought by the quantum algorithms, and you can think of what is doable in the near term, which means the principle in the near term is to use qubits the way they are now, which means they have some noise. And can I do something with a qubit that is noisy and put it on top of a high performance quantum computer? So we know that some algorithms can provide some really a lot of speed up soon. And for instance, this is an random number generator, which could be one of the shortest term application of quantum computer. And there are some variational algorithms where we don't really know yet how much speed up they're going to bring to the industry. And then in the long term, there are a lot of, now the algorithms are well sorted, and we know that they will provide some acceleration, but the price to pay to benefit from this acceleration is that it requires error correction, and this error correction is not yet implemented. So the idea of this introduction is that you understand that there are a couple of algorithms, especially the Hamiltonian simulation, the HHL algorithms, and the Shor algorithms, where we know for sure that they exhibit a exponential speed up with respect to classical computing, but they are not yet implementable because we do not have quantum error correction. So they are for the future. But still, we would like to see if it's possible to benefit from quantum computing advantage now, and that's the reason why there is a lot of work on noisy qubits and to see how much they can bring. And just to show you an example on a discussion on a variational algorithm, which is a noisy one, which take advantage of quantum algorithms and put it close to a classical computer, and it's called quantum approximate optimization algorithm, QAOA, and these are two publications. They are talking about the exact same algorithms, and one is by Rigetti. Rigetti is a quantum startup fabricating superconducting qubits, and which already sells prototypes. And Rigetti, with these algorithms, says that the QAOA algorithm will be an effective method for solving interesting problems on near-term quantum computers. And if you go to the paper, they've got a lot of data, and the conclusion is really it's a near-term application. And on the other hand, you've got Intel working on the exact same algorithm. And for them, the QAOA will always be, so they compare the time to solve, they compare the time it takes to solve a problem with QAOA and with a classical solver. And the classical solver is always below the quantum algorithm, and they tell the conclusion is, oh, QAOA is not interesting in the short term. So this is really when I'm telling you the status currently is that we do not know if we can benefit on the short term about from the quantum computers, which are not perfect. But nonetheless, I was telling you that there are a lot of applications, and I took a few applications where numerical simulation is important and impacted. And one example is, for instance, in health. Currently, there are some studies to look at, to compute the radiotherapy optimization to minimize the X-ray dose, and this is a partnership with D-Wave and Roswell Park. Same D-Wave is looking at the computation of de novo proteins and polypeptides creation with an hybrid computing. And this is really using the quantum computer to perform simulation on the energy domain is currently having a lot of traction with the electrification of the vehicles, and EDF set up a partnership with Pasquale, which is a French startup, to compute, and this is a graph problem, to compute the optimization of the distribution of electricity in station to recharge electrical vehicles. And same for the energy. Daimler is putting a lot of effort in computation, in doing battery computation to optimize the length, the lifespan of the batteries. In the automotive, so to continue on the automotive market, the players are really investing a lot in for material simulation, for product line optimization, position optimization. We were talking about having cars moving around, and for electrical batteries. And I just put an examples of a few players in the automotive. We speak about BMW, Volkswagen, Hyundai, Porsche, and they all have a lot of interest for this kind of simulations. And now to look at the physics simulation, one of the first system that we can simulate with a quantum computer is the physics systems that behave like quantum systems. And this is, for instance, superconductivity. This is graphene light interaction, superfluidity, ferromagnetism, and they are really well, these problems are really well adapted to quantum systems, and you let the quantum system evaluate in order to get your solution. And then you go more and more, you add some more complexity to have some carbon capture simulation. And this example is developed a lot by the French oil company Total. And there is some the physical simulation algorithms allow to describe a chemical reaction, and they go up to the protein interactions in order to sustain new drugs discoveries. And as I was saying, it's more and more complicated in terms of number of qubits. To provide you with some numbers, currently we, sorry, excuse me. Sorry, there is some noise behind me. Excuse me, there was some noise at home and I wanted to be more quiet. I go back to the presentation. Okay, so we were talking about the more and more complex systems, and to provide you with numbers, today we can simulate systems which have roughly below 100.
Madame Vinet, on ne voit plus,
yeah.
On voit plus vos transparents disparus. Le partage a dû être arrêté, peut-être, je pense.
Ok, je recommence.
Merci.
Est-ce que c'est bon là?
Ça s'en vient. Il y a un problème avec le screen sharing, ça s'en vient, c'est long. Non, ça ne vient pas.
Ça vient.
Vous pouvez l'arrêter et le repartir, voyons.
Ben, j'ai arrêté. Alors, j'ai arrêté. On recommence. Tout l'écran. Partager. C'est bon là?
Non, on ne voit toujours pas. Il y a écrit Maud Vinet a started screen sharing. Mais... Christophe, peux-tu voir de ton côté? Bien.
Je me déconnecte et je recommence.
Ok, allons-y comme ça. Pas sélectionné ça.
Donc, ça, c'est juste simultané. Regarde dans les options avancées, il y en a un qui permet à l'autre personne.
Ouais, mais là, elle s'est déconnectée. Là. D'habitude, ça marche très bien avec ça. Là. On n'a pas besoin de faire autre chose. Comment ça se fait qu'il était en haut et qu'elle a réussi à partager? Je sais pas. Là, elle s'est déconnectée et elle va. Elle s'est déconnectée, elle va rentrer.
On dirait que le problème technique de chez elle, elle devrait déjà être. Ah, elle revient. Mais là, en autre.
Attends. Nous revoilà. Donc, Marc, tu dis que c'est où qu'il faut appuyer parce que là, je ne vois pas beaucoup d'options disponibles. Hein. Madame Vinet, peut-être fermer peut-être le diaporama. Vous étiez peut-être en mode présentation, peut-être faites Escape pour sortir du mode présentation de PowerPoint, puis de repartir.
Ben, j'ai essayé de ça. C'est bon là?
Non, on n'arrive pas.
Et vous voyez quoi?
On voit un écran noir avec écrit Maud Vinet à started screen sharing, mais c'est ce qu'on voit d'habitude. Ah, ça y est. Ah, c'était revenu là.
Ah mince, bah, j'attends, je suis assez patiente alors, j'attends.
Ah voilà, c'est bon. Là, peut-être mettez-le. Voilà, parfait. C'est revenu. Merci.
Ah, je suis désolée.
C'est pas mon faute.
Du coup, là, c'était, oh no, sorry. It was just to say that the more qubits we have, the more complex we will be able to simulate proteins, and this is really a promising application to help with material, generally speaking, design. And I mean, I focused a little bit on this application because to me, when I was a student, that was really meaningful for me to be able to simulate Navier-Stokes equations, which is really useful in many of the fluid mechanics problems, and is one equation that, for instance, Airbus is really using a lot to optimize their design of planes, and they have raised a quantum challenge for you to use quantum computer to help solving these nonlinear partial differential equations. And there again, theoretically, quantum computer find a huge application to help solving these equations. Okay, so that was to talk about the applications. Now we've got applications, and so there is a whole traction of the whole industry to and the whole research fields to find ways to use this potential. And there are some questions regarding how software. So we've got two parts now to be able to. We have spoken about the algorithms level. Now to be able to exploit this potential, there are two domains that need to be developed. On one hand, we need the softwares, and on the other hand, we need the hardware that is able to run the quantum software. And I asked some colleagues from CA who are really doing research in quantum software, their challenge. What do they need? What are the challenges to write quantum softwares? And one of the biggest challenge they have is that you cannot access the value of the bits while you are running the program because of the non-cloning theorem, which tells you that you cannot copy the value of a quantum bit, because if you copy the value of the quantum bit, it means that you've lost the quantum information. So you cannot use the usual debugging systems of the softwares. And basically, there are all these questions: how to productively write quantum programs, how to ensure their quality, how to compile them efficiently, how much hardware agnostic can we be, how to ensure the correctness all along. All these questions have to be reconsidered with the advent of quantum computing, and there is some recreation of what was taken for granted since 60 years in the classical case. And you see, for instance, where is my, okay, this is the software, kind of a representation of the software of the full stack, where you start by the hardware platform, and the hardware platform is controlled by qubit controls, and on top of that you've got the software stack, which have an intermediate representation. You've got a compilation, and then you've got high-level languages and the algorithms we were talking about that are used to solve certain class of problems that relates to applications. And the question, you see that there is an overlap in the arrows here to decide up to where should we take into account the specificities of the hardware. And there is a consensus now to go quasi up to the compilation, because depending on the architecture, the way you will implement the compilers is going to be affected. And just to detail an effort that is made in CA by my colleagues from Paris, and that is an effort that is a worldwide effort. It's to put in place a formal verification softwares that allow to certify that the software provides the right answer. And this effort requires a co-design between the objects, and to define the object language semantics, and leads to uses deductive verification. And there has been a first formally verified implementation of a Shor algorithm. So now that's to conclude on this first part on how the software scheme and the architecture, the computing architecture is affected by the change of paradigm. And to summarize, if we compare a quantum computer in a classical computer, the code is clearly separated from the data in the von Neumann architecture. I'm not talking about in-memory computing. and there is continuous input and output of data. We can stop the code and start again. And there are several levels of memories, whereas in a quantum computer, you can just emulate the code on a classical machine, but with a small number of qubits, because then that's the promise of quantum computing. It's overwhelming. There is no more classical computer to check what is doing the quantum computer. We cannot stop the code and measure the qubit register, because then the computation is finished. We can't, it means we can't continue execution. We must restart all program all over again to move to the next sequence of gate. And just to notice that most Neumann functions handled by classical are handled by classical computer to drive the quantum accelerator. So the quantum accelerator is not doing everything. It needs a classical computer close to it. So that was to provide the big principle. And now you understand why there are so many applications and why there are so many people that are involved in quantum computing at so many levels, because it needs redevelopment of a lot of methodology that were taken for granted earlier. And I was at the beginning talking about close future applications and longer term applications, and longer term applications where the quantum algorithms have for sure an quantum speed up with respect to classical computer. They require to have quantum error correction, because if you take the numbers, these algorithms to beat classical computer, they need roughly 1,000 qubits, and these 1,000 qubits, they will be manipulated during millions or billions of operations. And there is definitely no physical system that have this precision. So millions of errorless operations require quantum error correction protocols. And like in classical computing, quantum error correction protocols, they rely on redundancy and they use entanglement. And the consequence of using quantum error correction protocols is that there is an overhead in terms of physical qubits to define what is called logical qubits. And the logical qubits are the qubits that are manipulated at the logical level. And typically, one errorless logical qubit requires roughly 1,000 physical qubits. And now we will see where we stand in terms of hardware. So from the software perspective, we have seen that there are many opportunities and people are making as if the hardware was going to arrive. Now we're talking about the hardware, and the question is, how do we fabricate the quantum computer that is going to be able to implement the quantum softwares? Well, there are many experimental platforms that allow to fabricate qubit. A qubit is just a two-level system that can be put into superposition and that we can entangle. And there are several systems like the atoms, the superconductors, the photons, the silicon qubits that demonstrate good qubits. At the physics level, they show very nice properties. And I have summarized the properties of a couple of experimental systems. The size of the qubit, the fidelity of the qubit, which is a proxy for the quality of the qubit, the speed of the qubits, which is important when we want to perform millions of operations to offer competitive runtime. The variability tells you how different from another are two neighboring qubits. So basically, it tells you the complexity of fabricating them. The temperature of operation tells you how much engineering, how much cryogenic engineering is going to be required. So what you observe now, if you look at them, is that in size, there is a lot of there are orders of magnitude in size between the different qubits. There are 12 orders of magnitude between the trapped ions and the spin qubits. And it can, when there are just a few qubits, you don't mind. But when you want to have more than, when you want to have more than 100,000 qubits or more, or roughly close to 1 million qubits, you begin to be very interested in the size of your qubits. The quality, the fidelity of the qubits, you want to be above 99% for all gates to be able to implement quantum correction. And this is true for superconductors, spin qubits, and trapped ions, and photon have a specific way of doing error correction. So basically, what you see is that there are a couple of candidates which have demonstrated qubits. And the question is now which one are going to be able to go to large scale to fabricate machines that we want to implement the complex algorithms. And okay, finding answers to this question. There are both startups or private companies, and there is a lot of involvement in research, and really people are looking at all the, well, at least at a lot of systems to implement this large-scale quantum computer. But and it's going fast, and the fact that there are so many people is really pushing the state of the art. And for instance, I made a snapshot of some qubit figures of merit in 2021 and some in 2022. And for instance, you see that the number of operational qubits is increasing in all the platforms. The supraconductor, they went from 65 to 127, and it was in October 22, and just in December, IBM announced 433. And the same for the cold atoms are also increasing, the ions, everybody is increasing. And not only the number of qubits is increasing, but also the quality of these qubits. Now all the systems, and that was the table I was showing you, all the systems have passed the quantum error correction thresholds, meaning they're all above 99%. So what it tells you is that the quantum computing hardware is really improving fast. And I just wanted to yeah, that's what I wanted to talk about. I just wanted to highlight the fact that we've talked about the fact that the quantum computing power is proportional to the qubit number. And now if we want to have an impact, we say that we want to have more than 100,000 qubits. And what would be nice also is that the complexity is not too big, so that we can provide an access to a wide range of industry. And that's the objective, and I went fast, that the promises of silicon based quantum computer, because the qubits made of silicon are small, they go fast, and they have good fidelities, and really the fact that they are small and they reuse the semiconductor industry potential allow them to promise a lot of qubits and in a small size. And currently I put some other systems to show you what is the complexity today. Today, this is a picture of Pascal machine with Rydberg atoms. And currently the atomic system, they are around 1000 qubits, but they don't know how to increase too much, how to increase the number of qubits without duplicating the machines. The systems, they have started from the labs, and now the extrapolation to go to millions of qubits is not straightforward for the atoms. And for the superconductors, the extrapolation will require a lot to handle big cryostats. And basically the total cost of ownership, the complexity of the system is exponentially complex when the number of qubits is increased. So basically today we have a dilemma where we've got, and I'm going back, we've got spin qubits which have not demonstrated a lot of qubits, but which are very promising on the long term. And on the other hand, we've got the systems that are very that have demonstrated a reasonable amount of qubits, and they have a hard time figuring out how they are going to build their machines with millions of qubits. And to finish the presentation, I just wanted to, so that's the hardware status. We've got the systems that were in the academic labs, and they are currently around a few hundred of qubits, and they claim that they can go to 1000 qubits, but their roadmap to go to larger numbers of qubits are struggling with complexity. And on the other hand, you've got the silicon spin qubits, the qubits based on silicon that have demonstrated only a few number of qubits, and that can go and they carry the promise to be able to fabricate billions of qubits. And why can they do that? And that's going to be the end of the talk. They can do that because they rely on the semiconductor industry, and the semiconductor industry allows to fabricate billions of transistors that are used in our digital devices on one hand, and on the other hand, semiconductor industry can fabricate integrated circuits, and these integrated circuits have the potential to efficiently control and program millions of qubits. And the fastest way to leverage the semiconductor industry potential is to start from an existing transistor technology, tune it in order to build qubits, and then you can fabricate arrays of qubits, and you control them thanks to transistors that are at the periphery of the qubits, and you reuse a lot of knowledge of the classical computing industry. Up to the fact that you can do quantum integrated circuits, and they look like classical mother card of our computers. and we're late. So I think what I will do is that I will give you the slides, and there are some details on how we go from transistors, from basic transistors to qubits. We basically cool them down, and by cooling them down, we are able to trap single electrons, and then by applying magnetic field, we're able to create a two-level system. And this two-level system, by applying an alternative magnetic field, we're able to really control and rotate the spin of these electrons. And just to let you know that these silicon spin qubits have already been demonstrated, and they have been demonstrated in classical technologies that are also used to demonstrate transistors. And the next step now to leverage the potential of the silicon spin qubits is really to take advantage of the semiconductor industry. And just now to conclude, I have talked a lot. I have talked about the software. We started by the software and the challenges to build software that are quantum softwares. We have spoken about the qubits and how to make the qubits and where does the hardware stand. And you've got to have in mind that in between there is a lot of electronics that helps controlling the qubits and implementing the software. And these electronics, there is some research work currently to partition this electronics so that the feedback to allow quantum error correction is as efficient as possible. Last but not least, and I started, oh, it's in French. Sorry, I did. Last but not least, I wanted to talk about the quantum energetic initiative. I spoke at the beginning of the fact that quantum algorithms provide quantum speed up. And if you reformulate that, you can say that for a given problem, the number of operations is going to be exponentially decreased by quantum algorithms. And if you say that, you can think of, oh, maybe if I decrease the number of operations, I can save energy. And there is a lot of debate currently. And once again, this is talking about the status. It's a debate. Quantum energetic cost is an open question. People have different perspectives on that. And the reason why people have different perspectives is because there is no real machine currently. And so there is no data, and quantum error correction is not yet at the state of the art. But still you've got to be aware of this debate, and the key scientific questions around that are to be able to have a system view, to design a system that will minimize the energetic cost of quantum computing. And it's a system perspective at each level. And for instance, we were talking about the quality of the qubit. The better the quality, the less correction, the less quantum error correction we need, so the less electronics. But at the same time, if the quality requires to go to very low temperature, maybe it's not favorable from an energetic perspective. So the idea is really to solve this question and be able to have a system simulation of the whole stack. Yeah, so the quantum energy initiative has the ambition to create a worldwide community that is interested in working the optimization of the energy spent while we are doing quantum computing. And just to finish and to conclude, I wanted to highlight, to finish this status, I wanted to let you know how you can access currently quantum computers, and you can easily access them through the cloud. And there are OVH in France, IBM, AWS, Microsoft, and Google have a cloud offer, and depending on which cloud service provider you have access to, you can have access to different hardware. You can either have access to quantum bit emulation or to real hardware, depending on which cloud service provider you choose. And the question to finish is, will quantum computer replace HPC? The answer is definitely no. A quantum computer will expand high performance capabilities as coprocessor in hybrid classical quantum systems. And with that, I can take a few questions, or I'm already late.
Oh, it's okay.